Hi folks, today we're going to look at what's called a difference in difference model. A difference in difference model is an econometric technique that we use in order to measure the impact of a policy change. Typically we're going to be using panel data, which means that we're going to have multiple observations over multiple periods. And so for example, a panel data set might consist of all the states in the United States measured over a 10-year period. So for each state there's 10 observations, 10 years. And so you'd have 50 states times 10, which would be 500 observations total. The problem that we run into is that in economics we would like to do randomized trials. In other words, we would like to sort people into two different groups randomly and then use the policy change to figure out whether or not those that were subjected to the policy change had an impact associated with them. And unfortunately in economics we usually don't have the opportunity of doing randomized trials because oftentimes a policy that gets enacted, it's enacted for everybody all at the same time. And so what we end up with is a measured effect of a policy on an outcome variable that may be the sum of the effect of the policy change in addition to whatever the overall trend is. And so if there's a trend that's occurring, it's going up over time, and then we implement a policy change, we might associate both the policy change and the addition to the trend to the policy change. And so in order for us to actually measure the impact of the policy change all by itself, we have to do what's called a difference in difference model. And you're calculating the differences in the differences over time. So typically we don't have the opportunity to do one of these randomized experiments where people are randomly subjected to the new policy. And so this is an econometric technique that we can use to try to simulate that. This comes from a paper by David Card and Alan Kruger, and this paper is now about 20 years old. There's a link inside the PowerPoint which you'll have available on CourseDen, but the link carries you to the original paper that Card and Kruger wrote. And their paper focused in on 410 fast food restaurants that were spread over two states, New Jersey and Pennsylvania. In New Jersey, they implemented a new higher minimum wage, and in Pennsylvania, they didn't change the minimum wage. And so that led to an opportunity for what we refer to in economics as a natural experiment. And so what we look at is how the change in the minimum wage laws impacted the unemployment rate. Remember, in theory, we always assume in economics that if you increase the minimum wage, and it's above the equilibrium wage, you're going to have a difference between the quantity of labor that's demanded and the quantity of labor that's supplied. And so there's going to be more labor supplied than demanded. This is going to result in excess labor, and we refer to that in economics as unemployment. And so the idea here is, in theory, if you change the minimum wage, if you increase it above a market wage, you're going to get additional unemployment in the economy. And so the problem might also be that the unemployment rate was changing over time in addition to the fact that they changed the minimum wage laws. And so you'd want to break those two apart to find out whether or not there was actually an impact on the unemployment rate as theory would predict, assuming that we were at a market equilibrium wage. And so a question that you might address here, if you read this paper, I would like you to read it and tell me what Card and Kruger, what did they find? Did they find that the unemployment rate went up? Did they find that it went down? And secondly, how did they support these conclusions? What statistical evidence did they use in order to suggest that minimum wages caused one thing or another? And so the difference in difference, also called diff and diff or DID, is a quasi-experimental design that uses longitudinal data from both a treatment group and a control group. And so the treatment group is the group that receives the change in the policy, the ones that are subjected to the policy change. The control group, those are the people who aren't subject to the policy change. And so in order to obtain an appropriate counterfactual estimate to the causal effect, counterfactual estimate to a causal effect, we have to incorporate both of these two groups. So the difference in difference is typically used to estimate the effect of a specific intervention or treatment, such as the passage of an unemployment law, the enactment of some specific policy, or some large-scale program change or implementation. By comparison, the changes in outcomes over time for a population that's enrolled in a program, or the intervention group, and the population that's not in that intervention group, which is called the control group. And so here's what it looks like graphically. Generally, you'd have two different groups, the green group and the red group, and the red group is subjected to the policy change. And so if the policy has some sort of impact, we would expect there to either be a vertical jump and the same slope, or there could even be a bending upwards or a bending downwards. It just depends on the impact of the policy. But in this graph, it would indicate that there's an increase in the variable of the outcome variable after the treatment occurs. And so what you see is that these two lines are effectively parallel until the treatment occurs, and then after the treatment they diverge from each other. And so what we're trying to do is measure the difference between this difference and that difference. This is the difference that we would have expected over time, given that they increased at the same slope and there was no policy change. Given the policy change, however, we're expecting an addition to the slope over time, at least in this example we are. And so this piece right here represents that second difference. It's the difference after the policy change. So there's some assumptions that we have to take care of. And all the models that we deal with, there's always assumptions. And so these assumptions are generally classified into three categories. So in order to estimate any kind of causal effects, in order for our beta coefficients in our regression model to be causal, we have to satisfy these three assumptions. They're called exchangeability, positivity, and stable unit treatment value assumption, or SUTVA. Exchangeability just means that in the absence of the treatment, the observed differences between the treatment and control groups remain the same. And so that's where if we look back at that graph, that's where we got those two parallel lines. Without the treatment, they're going to stay basically the same distance apart over time. They don't have to be exactly the same distance, but in a reasonably sized sample, they should be relatively close to the same distance apart over time. Positivity, this just means that any individual in the sample has a positive probability of receiving the treatment. So it's almost as if it's a potential that they could be randomly put into one group or the other. Positivity violations occur when certain subgroups in a sample either very rarely or never receive access to the treatment, or they don't receive the treatment. So in this case, what we would be thinking about is they don't receive the policy, or they're not subjected to the policy ever. Good. We'll deal with that. SUTVA, or the stable unit treatment value assumption, suggests two different individual items. So SUTVA has two different components to it. The first component is that applying the treatment to one observation doesn't affect another observation. And so if you get a treatment, if somebody is treated, that treatment doesn't have a spillover into another observation that isn't treated. And so there's no feedback loop that can potentially go on. There's also no spillover effects that can happen. Secondly, there's only one single version for each treatment. We don't have multiple levels of the treatment, and we don't have multiple treatments going on, because that would significantly complicate the regression that you'd have to create. Okay, so to explain a little bit better about one of the assumptions, we assume that there's a constant difference between the two, absent the treatment. And this is also referred to as the parallel trend assumption. And all this means is that you tend to have the same distance apart until the treatment occurs, and then things can change. This category, I mean, this graph here satisfies the parallel trend assumption because you can see that there's close to a constant difference until the treatment occurs, and then after the treatment occurs, the slope changes for the dark black line, and then they go back to being parallel again, but they're on the opposite sides of one another. Okay? And so this treatment here changes the level of, but not the slope of, the outcome variable. On the other hand, if you look at this second graph, this is a violation of the parallel trend assumption. Because what you can see is that during the period just prior to the treatment, the red line is falling where the blue line is rising. And so they're diverging from each other already. This would violate the parallel trend assumption, and it would mean that we could not conclude, if we ran the difference in difference model, that these two, that the differences that we calculate would be due to the policy change. It could be due to more things than that. And so we can't specifically identify that policy change. The simple difference in difference model is fairly easy to do using SAS or any other statistical package. Usually what you have are 3 different variables plus other right-hand side variables that you would include in order to control for whatever you believe should be in the model. The first variable that you need is a dummy variable that indicates which jurisdiction has the policy or which jurisdiction adopts the policy. And so it doesn't matter when they adopt it. If that jurisdiction adopts a policy, they get a 1. If they don't adopt the policy, they get a 0. And so, for example, if a state adopts a policy but its neighbor doesn't, for all observations in your data set for the first state, you'd put a 1 in, and for all other states that didn't adopt the policy, you'd put in 0s for all their observations. Okay, and so that's the policy dummy. There's also a time dummy. The time dummy identifies the period in which the policy is in effect. And that's true for all jurisdictions. And so even if we're talking about all 50 states and only one state had the policy in effect, for whatever periods that the policy is in effect, you give that state and every other state a 1, and for all other periods it's 0. Okay? The third term that you would include in the regression is the interaction of the time and the policy dummy. The way you get that interaction term is by multiplying the policy dummy with the time dummy, and the only time it will be 1 is when the policy dummy equals 1 and the time dummy equals 1. If the policy dummy is 1 but the time dummy is 0, they multiply out to 0. The same is true in the opposite direction. If the time dummy is 1 and the policy dummy is 0, they would multiply out to 0. So the only situation in which you're going to get a 1 there for the policy time interaction term is when both the policy and the time dummies are 1. And down at the bottom here, you can see this is the interaction term. This is the term that we're interested in most when we run the regression. Whatever the direction this variable is going in, that tells us the causal impact, positive or negative, of the policy change that we implement. Now keep in mind, all our assumptions have to hold for this to be true. But if all the assumptions hold, then this right here is the causal impact of whichever policy you implement and measure. Okay? These other variables are included in order to control for time and for policy independent of this interaction term. And other variables can be put in here as well. You can include demographic variables, you can include variables about state population, about state average income, median family income, any other number of variables that you might want to include in order to measure the impact of the outcome of the policy. So let's pick a recent policy. This is actually a fake policy. I decided to use this because, interestingly enough, we're in the midst of an outbreak of coronavirus. And so let's suppose that 8 days into the coronavirus outbreak, the state of West Dakota implemented a ban on beer pong in groups larger than one person. In East Dakota, they did not implement the same ban. And we're going to assume that there's no other policy changes that occur, no other major policy changes that occur around that same period. And that way we have the opportunity to see how this new policy will affect the new numbers of coronavirus cases in each of those states. Okay, and so here's what the data looks like. I put all the data up here. Generally, and I've also got the SAS program that will show you how to run the difference in difference model, and I also include a link to the data here. So all you have to do is click on this, it downloads the data in the SAS program, you can run it and see the output. You're going to use this program and use what you learn from this program to do an exercise at the end of this PowerPoint. Okay, so we're going to input the beer pong data. This gives us the variable names. We've got the state name, the number of new cases, the time variable, the policy variable, and I also include a day variable, which tells you how many days into the outbreak we are. And so the reason for that is there could be a trend, and we want to control for that trend as well. A time trend, that is. Okay, so download this, open it up in SAS. You don't have to download the data per se. All you need to do is download this. It's got the data in the program. Okay, so when we run this, we can create the graph that looks at the difference in the two different states and their additional numbers of patients per state. And what we see is that in the first few days, up to about day 8, West Dakota has more cases and a higher growth in cases than happens in East Dakota. I should say a larger growth in cases in West Dakota than in East Dakota. The line here, the vertical line, represents the point at which we enact the new policy of no beer pong in groups larger than one. So you can play by yourself, but you can't play with a second person. So after this, you can see that the number of new cases in West Dakota falls below those in East Dakota, and then they maintain pretty close to the same number of new cases throughout the remainder of the series, up to 35 days. Okay, and so I created this data set. This is not based on anything that has actually been measured out there in the public, and there is no beer pong ban that's going on right now in either of the Dakotas, north, south, east, or west. And so this is just to illustrate the point. And so remember here, we have a dummy variable, time, and this indicates the period when the treatment was in effect. We've got a dummy variable called policy, and this identifies the group or the state that's exposed to the treatment. We've got an interaction term, which is a dummy variable also. It's an interaction between two dummies, and it's between time and the treatment. And it should only equal 1 when both time equals 1 and the policy equals 1. Okay? Additionally, for this data, we also include a count variable called day, and that's just the number of days from the start of the outbreak. And it controls for any upward linear trend in cases within the state or within both states. And here's what the results look like. Now, first of all, don't get too excited about the strength of results. We got a 99.75% adjusted R squared and a 99.76 R squared. Remember, I created this data. I wanted it to look really strong in its relationship so that it would jump out at you. It's not because I found this data online and we're having an outbreak because of beer pong. We're not. The variable policy equals ones for states that eventually adopt the policy, i.e. West Dakota always equals 1. East Dakota, because it never adopts it, always equals 0. This variable estimates the impact in Western Dakota over Eastern Dakota, holding all other things constant. Okay, so it measures the impact of adopting the policy, holding other things constant. The variable of interest, however, is the interaction term, policy time, or policy times time. This indicates that enacting the new policy, no new beer pong, or no beer pong, actually reduces new cases by an average of 24.5 cases per day. Okay? The impact is significant, and so if we look down here, here's the 24.5 and it's negative. The impact is significant at greater than the 1% level. It's actually 0.0001, and you got that little less than sign there, which means it's a good bit less than 1/10,000th instead of 1/100th. Okay, so it's very significant. T-stat is a minus 18.07. If we assume that there's no violations in the assumption, this is the causal effect of the policy. That the policy itself reduces the number of new infections by about 25 over not having the policy. Now there's a lot of other things that you can do using the difference in difference model. There's a lot of different issues out there that people may want to look at. Some may already be in the works for some researchers out there. Specifically, you could look at state level marijuana decriminalization and its effect on crime rates, jobless rates, incarceration rates, any number of things that people think of as being positives or negatives that are associated with decriminalizing marijuana. You can also look at changes in state sales tax rate and how it affects county level retail sales in border counties on either side of a state line. One of the things that happened here in Georgia a decade or so ago is that Alabama drastically increased its sales tax relative to Georgia, and there was concerns about cross-border shopping and how that cross-border shopping occurred. And so this is one way that you could try to see how the impact of a change in a sales tax plays out in the retail sector. Another thing you could look at is, suppose one state enacts a brand new healthcare law, but a neighboring state doesn't do that. How does that impact the health of the state? How does it impact the number of people that seek medical attention? Lastly, but not lastly in total, just lastly as part of the list that I have here, the effectiveness of a specific marketing campaign on product sales before and after the release of the campaign. Obviously, you don't do a marketing campaign if you think it's going to have no impact on sales. If you did, you could just save the money and not actually do the marketing at all, and sales will stay the same. But generally, people spend, or companies spend a lot of money marketing their products. You could look at specifically a Super Bowl ad and see whether or not there was a positive impact on a Super Bowl ad. But what you'd also need to know is what were the sales before and what were the sales after. You would assume that the sales as compared to a competitor might actually start trending apart if the Super Bowl ad was effective. There's other situations that you might want to use a difference in difference model. For example, you might want to use one in the situation where you have a binary dependent variable. Up until now, everything that we've looked at has been somewhat continuous. The number of new cases of the coronavirus, although those are individuals and they're discrete, if you get enough of them, it starts looking more and more like continuous data. On the other hand, a binary discrete choice is definitely not continuous. Oftentimes what happens is the first pass at it looks like an ordinary least squares model using what's called the linear probability model. That's just using OLS on a with a binary dependent variable. Okay, and so that makes it easier to implement. It also makes it easier to use for interpretation, but it places some limitations on your ability to do prediction. And the reason it does is because it's not bounded by 0 or 1. So if we're talking about, say, whether or not something survives or not, then you can't have lower than a 0 probability of survival, and you can't have larger than 100% probability of survival, except for the linear probability models actually allows for predictions that are outside that range. And so it does create some prediction problems there, especially in those areas where it's bounded. Another thing that you might want to try is using a logistics model. And the problem with using a logistics model is that it requires additional coding in SAS in order to make it work. And so we're not going to cover that in this example, but know that you've got a standard model, a standard difference in difference model that you can now perform using ordinary least squares on a continuous variable. And you've also got the ability to handle a binary discrete choice using the linear probabilities model, with a caveat that you don't want to try to predict things that are too close to 1 or too close to 0. So here's an exercise for you. Georgia passes a bill which makes employer-provided health insurance tax deductible. In other words, it makes it less expensive for the employer to provide. Assume that in the year after the bill passes, the percentage of firms offering health insurance increases, say by 50%, as compared to the year before the bill was passed. In order to estimate the impact of the bill on the percentage of firms offering health insurance, we could just simply use a before and after analysis. In other words, before the bill, no change. After the bill, there was a 50% increase. But the 50% increase includes both the effect of the change in the policy and also the effect of the time trend. Okay? And so we want to break it apart and find out what the actual impact of the policy change was, taking out that trend. So the problem is that there could be a trend already underway for more employers to offer insurance. With that current information, it isn't actually possible to identify how much the new Georgia law or the time trend, either one of those, contributes to the increase in the firm's offering of insurance. So, the link below contains a data set with 4 states. Only Georgia has passed the bill which in this data set took effect in 2009. I want you to use SAS to estimate the difference in difference model of percent provide. That's the dependent variable. I want you to use a time trend variable that's similar to what we used in the previous example. Here's a hint. One of the variables in the data set can already be used directly as the time trend variable. Figure out which one those are. You're going to have to create a couple of variables in addition to that. You need to create a variable of the time when the policy is in effect and when it's not, and you need to create a variable of the state that has the policy in effect and those states that don't. And then you're going to have to create the interaction term. So you're going to have to do a little bit of lifting here in order to get through this project. But what I want you to do is estimate the impact using a simple difference in difference model with one added right-hand side variable, that time trend variable that we want to use to predict controlling for the trend over time. And then I want you to take that output, put it into a Word document, and upload it to the Dropbox for the difference in difference model. If you have any questions, I'm available by email. Send me an email directly. We're not on campus most of the time, and so don't bother picking up the telephone, because I cannot forward my telephone to my cell phone or to my home phone. For some reason, my phone doesn't work that way. But give me an email, and I will try to get back to you within the day. Thanks a lot, and look forward to more videos in the future, because we are now online.